This video is about polynomial congruence and its similarity to integer congruence. Just as polynomial rings are very similar to the ring of integers, so a polynomial ring modulo an ideal generated by a polynomial is very similar to the ring Zn. Our goals for this video are to review how the ring of integers Z is similar to the ring of polynomials with coefficients in a field. To construct the quotient ring of polynomials with coefficients in a field, modulo the ideal generated by a polynomial with coefficients in that field. To show how that quotient ring is similar to Zn, and to work a few examples and concept checks. We will assume familiarity with the definitions and basic properties of the integers, of quotient rings, of principal ideals, and of polynomials with coefficients in a field. We will use the following notations and conventions. All the rings in this video are commutative rings. Thus, every ideal is two-sided. We will use this notation for I as an ideal of R. Additionally, Z will stand for the ring of integers. Zn will stand for the ring of integers modulo n. Q will denote the field of all rational numbers. And F brackets x will denote the ring of polynomials in the indeterminate x with coefficients in the field F. For a field F, the ring of polynomials with coefficients in F is very similar to Z in many ways, including the following. All of these should feel like review. First, in the definition of divisibility. In the division theorem, both for integers and for polynomials. In the definition of the GCD. In order to make the GCD of two polynomials unique, we will insist that the GCD is a monic polynomial with coefficients in the same field. We have Bézout's lemma for polynomials, which says that the GCD of two polynomials can be expressed as a linear combination of the two polynomials. And, moreover, that any linear combination of the two polynomials is a multiple of the GCD. I recommend that you pause the video and review these important results before going on. Some more ways that the ring of polynomials is very similar to the ring of integers. The definition of a prime integer is very similar to the definition of an irreducible polynomial. We have Euclid's lemma for integers, which translates exactly over to Euclid's lemma for polynomials. And the proof is analogous. We have unique factorization for integers and unique factorization for polynomials. And these are analogous as well. And finally, every ideal of Z is principal, i.e., any ideal of Z is generated by a single element. And the same is true for polynomial rings. If I is an ideal of a polynomial ring with coefficients in a field, then I is generated by a single polynomial. We are going to be going over a bunch more facts and definitions that are exactly analogous to corresponding familiar definitions and facts about integers. The facts will all have analogous proofs, which you are urged to write out as practice. And if you get stuck, look at the corresponding proof for integers. So by item 8 in the previous list, we can work with the quotient ring of polynomials just as we work with Zn. So here's item 9. The definition is exactly analogous to the definition for integers. Let f be a field, and let p of x be a non-zero polynomial with coefficients in f. Let f of x and g of x be polynomials with coefficients in f. we say f of x is congruent to g of x modulo p of x, and we use the same notation as we do for integer congruence, if p of x divides f of x minus g of x. As an example, let f of x be equal to x cubed plus 3x squared plus 2x minus 5 with coefficients in the rational numbers. Then f of x is congruent to x minus 8 modulo x squared plus 1, since we can observe that f of x can be written as x plus 3 times x squared plus 1 plus x minus 8. In other words, f of x is a multiple of x squared plus 1 plus x minus 8. Item 10 says that addition and multiplication of polynomials modulo p of x are independent of the choice of representatives. That is, if you add f of x plus g of x, or if you add h of x plus k of x, where h of x is congruent to f of x and k of x is congruent to g of x, you will get the same congruence class, mod p of x. And the same is true for multiplication. So this gives us another way to get the result in example 1. X squared plus 1 is congruent to 0 mod x squared plus 1, and therefore x squared is congruent to negative 1 mod x squared plus 1. Thus, we can replace every instance of x squared in f of x with negative 1. You can see here x cubed is equal to x times x squared, so that becomes x times negative 1. X squared here is replaced with negative 1. And when we simplify, we get x minus 8. Item 11, fact. Congruence modulo a polynomial is an equivalence relation on the ring of polynomials with coefficients in a field F. So we can work with congruence classes. The congruence class of f of x modulo p of x is the set of all polynomials that are congruent to f of x, mod p of x. Item 12 is another fact that is analogous to the corresponding fact for integers. For p of x, a polynomial with coefficients in f, the set of all equivalence classes modulo p of x forms a ring called the quotient ring of polynomials modulo the ideal generated by p of x. A remark on notation. Recall that for an ideal I of a ring R, the quotient ring R mod I consists of cosets A plus I, where A belongs to R. So the congruence class of f of x modulo p of x is actually a coset f of x plus the ideal generated by p of x in the quotient ring, which is very similar to the notion of the congruence class of an integer a modulo n. It's actually a coset a plus nz in the quotient ring z mod nz, which we usually denote by zn. But for ease of notation, we will use the congruence class notation with the brackets rather than the coset notation, just as we often use the bracket notation for an element of Zn. Now we come to a very important result, the uniqueness of principal representatives. Item 13 is both a fact and a definition. The class of a polynomial f of x in the quotient ring of polynomials modulo the ideal generated by p of x contains exactly one polynomial r of x with coefficients in f, which is either the zero polynomial or a polynomial whose degree is strictly less than the degree of p of x. And this polynomial r of x is called the principal representative of the congruence class. This follows from the division theorem that says that we can divide f of x by p of x and get a unique quotient and remainder polynomial. And the remainder polynomial, r of x, is the principal representative of the congruence class. So looking at example 1 again, this is the one where f of x is equal to x cubed plus 3x squared plus 2x minus 5 with coefficients in q. Let p of x be equal to x squared plus 1. That's our modulus polynomial. We saw that f of x is congruent to x minus 8 mod x squared plus 1. And sure enough, x minus 8 is of degree less than 2 and is congruent to f of x. And we can get it by performing polynomial division. Divide f of x by p of x and get quotient and remainder. And here's our remainder, x minus 8. Here we come to our first concept check. Pause and explore. I urge you to pause the video and work out the solution for yourself before proceeding. Let p of x be equal to x cubed plus x squared plus 4x plus 1, considered as a polynomial with coefficients in z5. Find the principal representative of the congruence class of f of x, where f of x is equal to 3x to the 4 plus 2x cubed plus 4x squared plus 1. Pause the video and come back when you are ready. So here's our solution. We can perform polynomial division to see that f of x can be written as 3x plus 4 times p of x plus 3x squared plus x plus 2. So 3x squared plus x plus 2 is our remainder polynomial, and we'll call that r of x. Notice that the degree of r of x is 2, which is strictly less than 3, which is the degree of p of x. And that f of x is congruent to r of x mod p of x. Thus, the class of f of x is equal to the class of r of x, and the principal representative of this class is r of x. By uniqueness, that's the only one. We have results about existence of inverse elements. Item 14, fact. A non-zero class of f of x in the quotient ring of polynomials modulo the ideal generated by p of x has a multiplicative inverse class, the class of g of x, in the quotient ring, if and only if the GCD of f of x and p of x is equal to 1. And as a corollary, p of x is irreducible over f if and only if every non-zero class in the quotient ring has a multiplicative inverse. In this case, the quotient ring forms a field. And again, these are exactly analogous to the results for integers. So looking at example 1 yet again, note that p of x equals x squared plus 1 is irreducible over q. Using the Euclidean algorithm for polynomials, we've already seen that f of x is equal to x plus 3 times x squared plus 1 plus x minus 8. If we then divide x squared plus 1 by x minus 8, we get a remainder of 65. This is a constant polynomial of degree 0. So we know that this is going to be our last non-zero remainder. So the GCD of f of x and x squared plus 1 is 1, since it must be monic. And we can reverse the steps of the Euclidean algorithm to write 65 as a linear combination of f of x and x squared plus 1, and then divide through by 65 to get 1 as a linear combination of f of x and x squared plus 1. Note then that if we take both sides modulo x squared plus 1, This term, being a multiple of x squared plus 1, is congruent to 0 mod x squared plus 1. And therefore, f of x times negative 1 over 65 times x plus 8 is congruent to 1 mod x squared plus 1. And therefore, the inverse of the class of f of x in the quotient ring is the class of negative 1 over 65 times x plus 8. Here's our other concept check for this video. We're going to let p of x and f of x be as before. These are polynomials with coefficients in Z5. Part A, determine whether or not p of x is irreducible over Z5. And part B, if possible, find the inverse of the class of f of x in the quotient ring of polynomials with coefficients in Z5 modulo the ideal generated by p of x. So pause the video and come back when you have a solution. So here's our solution. For part A, we can check that p of x has no roots in Z5. There are only 5 elements to check, and you can just try them all and see that you do not get 0. So p of x has no linear factors by the factor theorem. Since p of x is of degree 3 and has no linear factors, p of x is irreducible over Z5. We've already determined that the class of f of x is a non-zero class because its principal representative is not 0. Thus, we are guaranteed that the class of f of x has an inverse in the quotient ring. For part B, again, we can use the Euclidean algorithm. As a reality check, our Euclidean algorithm should end with a non-zero constant here because we already know that the GCD of f of x and p of x should be 1 by fact 14. So we can reverse the steps of the Euclidean algorithm. I invite you to work that out for yourself if you haven't already, to get 2 as a linear combination of f of x and p of x. Then we need to express 1 as a linear combination of f of x and p of x. So we can multiply both sides by the inverse of 2 in Z5, which is 3. So we multiply both sides by 3. On the left-hand side, we'll get 3 times 2, which is 1 in Z5. And then if we multiply 3x squared plus 3x by 3, 3 times 3 is 9, which is 4 in Z5. We'll get 4x squared plus 4x times f of x. And in the other term, multiplying x cubed plus 4x squared plus 4x plus 2 by 3, and taking the coefficients mod 5, we'll end up with 3x cubed plus 2x squared plus 2x plus 1 times p of x. This second term is congruent to 0 mod p of x. So if we take the right-hand side mod p of x, we will get 4x squared plus 4x times f of x mod p of x. So 4x squared plus 4x is a polynomial that we can multiply by f of x and get something that is congruent to 1 mod p of x. That sounds like an inverse. So sure enough, the inverse of the class of f of x is the class of 4x squared plus 4x in the quotient ring of polynomials with coefficients in Z5 modulo the ideal generated by this p of x. By our previous result, this representative is unique. In summary, for a field F, the ring of polynomials in a single indeterminate with coefficients in F is very similar to the ring Z in many ways, including all of these. Numbers 1 through 4 that we reviewed at the beginning. Items 5 through 8 that we also reviewed at the beginning. One more remark about item 8 here. Any integral domain for which every ideal is principal is known as a principal ideal domain, or PID. And so what item 8 is saying is that both Z and the polynomial ring with coefficients in a field F are PIDs. In fact, as it turns out, a subcategory of PIDs is the category of Euclidean domains. A Euclidean domain is a PID for which we can execute a Euclidean algorithm. And it turns out that polynomial rings share that property with Z, that Z and polynomial rings are Euclidean domains. Being a Euclidean domain is a very restrictive criterion. Only some very special rings are Euclidean domains, which accounts for all of the similarities that polynomial rings share with the integers. It all stems from them both being Euclidean domains. This vocabulary of principal ideal domains and Euclidean domains are not commonly emphasized in undergraduate abstract algebra. But if you are interested in learning more about these structures, you can look elsewhere for more information. And our new fact, congruence modulo a polynomial is very similar to the definition of congruence mod n in Z. Addition and multiplication mod p of x are independent of the choice of representatives. Congruence modulo a polynomial is an equivalence relation, so we can form congruence classes. The set of all congruence classes, mod p of x, is the quotient ring of polynomials with coefficients in F modulo the ideal generated by p of x. Each class contains exactly one principal representative. The class of A of x has a multiplicative inverse, class of B of x, if and only if the GCD of A of x and the modulus polynomial is equal to 1. And our corollary, that the quotient ring of polynomials with coefficients in F modulo the ideal generated by P of x is a field if and only if P of x is irreducible over F. I hope you found this video helpful.